Hello calculus students, today is on volumes of solids of revolution. A solid of revolution is created when you take a region in a two-dimensional plane, like in the xy plane, and then you revolve it around some sort of axis to trace out the shape of a solid. You're going to see that region be revolved around the x-axis, although you could also revolve it around other axes. If you were to slice it, and look at the slice from the side, you'll notice we have the shape of a circle with a hole missing. We'll call this a washer shape. Now, if the second function wasn't used as a bottom boundary, when you revolve that region around the x-axis, it would have created a solid, and then a cross-section would have been circular. It would have been what we call a disk. Okay, and then our goal will be to find the volume of such a solid. Now, before we go too much further, I have a slide here. This is the first slide from your guided notes, where we're going to get some practice on how to establish different lengths from a curve to different axes of revolution. This slide here will be extremely useful in determining the correct lengths to use in our formulas. Okay, so we have some sort of function right here. Its equation is given 3y plus 1 is equal to 2x. Notice I don't have the equation solved for y, nor do I have it yet solved for x. Sometimes it'll be important for us to solve that for y, and sometimes it'll be important for us to solve that for x. Then we take an arbitrary point on the curve. We'll call it x comma y, and imagine that point varying along the curve. And at any position, we'll say its coordinates are x, y. Now, the x and y coordinates of any point that's in the first quadrant tell you how far that point is from the x and y axes. The x is always how far you are from the y-axis. So in this image, it's going to be this red length. That red dotted line has length x. And the second coordinate, the y, is how far the point is from the x-axis. And so this orange dotted length is going to have a length given by the y-coordinate. Now, of course, we are assuming that x and y are both positive because our picture is here in the first quadrant. And so for our purposes, x and y are also lengths. If you were in a point in a different quadrant, then you would maybe need to negate one of the coordinates so that it'd be positive. When I say that I want them to be interpreted as lengths, that just means I want them to be interpreted as positive. Okay, so in this table, we are going to figure out ways to express how far this arbitrary point, point P, is from different axes. Let's focus on how far the point P is from the x-axis. Well, that's a y-coordinate. So in terms of y, you would simply put a y there. How far is the point from the y-axis? Let's look at this one next. The point is x units away from the y-axis. And so that's going to go in the in terms of x column. Okay, so let's go back to the first row here and focus on how far we are from the x-axis. Well, the y-coordinate of this point can be determined from its equation by solving it for y. So we have a few steps you want to do. Isolate the y. So we're going to subtract the 1 and then divide by 3. So this y-coordinate in terms of x would be, we're going to 2x minus 1 and divide by 3. 2x minus 1 and divide by 3. So if ever you need to describe how long that orange line segment is, but you want to do it in terms of x, then you would say 2x minus 1 all over 3. And we have that length in terms of x. Similarly, let's look at the red line segment. Its length is just x, but if ever I want to express that in terms of y, then I'm going to have to take this equation again and solve it for x. The red line segment has length x, which could also be written as, and up here we just have to divide both sides by 2. That'll be 3y plus 1 all over 2. So looking at this table, the distance from the point P to the y-axis in terms of y is we're going to use this expression instead, 3y plus 1 all over 2. Now let's focus on how to express how far the point P is from the line y equals 4. Well, y equals 4 is a horizontal line. It's up here. So when we're saying how far the point P is from that line, we're actually after the length of this blue dotted line segment. Well, one thing that you're going to notice is that in this image, ultimately we're after 6 different lengths, and they're all color-coded. The vertical ones, which is the blue, the green, and the orange, their lengths are always given by y-coordinates or differences of y-coordinates. For example, if I take this point here and say how far apart are they vertically, you would say, well, this one has a y-coordinate of 4 and this one has a y-coordinate of 2.5, and you would subtract them to get a length of 1.5. All right, so you focus on the y-coordinates when you're trying to figure out vertical lengths. and you would focus on x coordinates when you're trying to figure out horizontal lengths. So right now we're on the blue, a vertical length, and we've already established that the orange has a length that we're calling simply y. Well, from the x-axis up to 4, that's going to be 4. So by basic subtraction, 4 minus y will be a good expression for how long the blue line segment is. Now that's how long that blue line segment is in terms of y. So that's going to go into this column here. If you want to do that same length but in terms of x, then you simply have to replace y with the rule 2x minus 1 all over 3. So then I would say 4 minus 2x minus 1 all over 3. Okay, let's do the green line segment next. We're trying to determine how far it is down to the line y equals -2, which is a horizontal line down here. In order to do that, there's a few different ways you can think about this. We've already established that this length we're calling the y coordinate, and we want to go an additional 2 units down from the x-axis. So now we can just add these together and say that the entire green dotted line is going to be y plus 2. And since that's in terms of y, we want to put that in the second column. Another way to think about this is to think along these lines. This point P is at a horizontal line that we're saying is at height y. And we're using a variable, not a constant there, because you're imagining that point P, right, moving along this curve, and it takes on different values as it goes up. The other line down here is y is -2. And when you want to figure out how far apart vertically are two y coordinates, you do the upper one, which is y, minus the lower, which is -2. And that winds up producing the same thing. So just another way to think about it. Now, in order to express that same length, but in terms of x, all we have to do is replace this y right here with the rule for its function of x. And that's how long the green line segment is in terms of x. Okay, now let's focus on the other horizontal ones. Let's do the black one next. Here we're determining how far the point P is from the line x equals 1, is simply how long is that black dotted line right there. If we already know that y-axis to the point P has a horizontal length of x, and we know that this length here is 1, you can see we could use subtraction to figure out the length that we're after. We'll do x minus 1 is how long that black dotted line is, and since that's in terms of x, that just goes in the first column. Now if I want to express that in terms of y, then all I have to do is replace this x with its function of y rule, which we expressed right here already. 3y plus 1 all over 2, that's the x, and then minus 1. Okay, now let's do the purple line segment. The distance up to the line x equals 6. Now I know that from y-axis to 6, that length is 6. And we also know that from y-axis to the point P, we're saying is x. Therefore, we can do some subtraction to figure out the rest of this. We would say the total length 6 minus the length x, and that gives us the length that we're after. And then, once again, to express this in terms of y, we just do 6 minus x, but change x to 3y plus 1 all over 2. Now, a second way you could think about this is imagine that we have a vertical line right here. This is at x equals 6. Then we have a vertical line through the point P that's at location arbitrary x. Now that will be moving, right? So imagine this line being able to move around as you do different points along this curve. But in general, when you know two vertical lines and you want to find out how far apart horizontally they are, then you do right vertical line minus left vertical line, right? So again, that produces this 6 minus x expression. Okay, now looking at this table, vertical line segments that we were after are all very simple expressions involving y. And then if you need to express them in terms of x, you simply change the y to the rule for the function in terms of x. The horizontal line segments are all easiest to describe in terms of x. But if you need to express them in terms of y, then you simply change x to its function of y, and you get these other versions. Now the formulas here, if you were to take a specific point, let's say this point here, the end point, we know its coordinates are 5, 3. If you were to take those coordinates and plug them into these formulas, you should get some answers that make sense. In fact, how far is the point 5, 3 from the x-axis? Well, it's 3 units away from the x-axis. And according to our formula here, you can do this one of two ways. You can either just plug the y-coordinate in right here and get that answer 3, or you can plug this x-coordinate 5 into this expression and see what you get. Right, 2 times 5 is 10, minus 1 is 9, divided by 3 is 3. So you get the same answer. You get 3 whether you plug x here, or you get 3 whether you plug y here. Okay, now let's move on to some formulas. the disk method versus the washer method. So let's say we have some sort of region, and as part of its boundary we have a straight line, and that straight line I'm talking about is down here, and we're going to revolve the region around that line. We're calling that the axis of revolution. And the axis of revolution, if it's one of the boundaries of your region, when you revolve this around that axis of revolution, it's going to produce a solid with no gap in the middle. Now in this case, horizontal strips would not be ideal because horizontal strips hit the same curve twice. Well, let's just do vertical strips through this. So if you were to imagine a vertical strip, I'll just draw one in sort of an arbitrary location, and imagine that strip being revolved around this axis of revolution, the dotted line. In this picture, that axis doesn't have to be the x-axis. And when you revolve that strip around that line, that strip is going to trace out the shape of a disk, something like this. And then the axis of revolution will go right through the middle of it. We're finding the volume of a solid whose cross-sections are all circles. And since I can find the cross-sectional area, if I can find the volume of this disk, then all I have to do is add up the volume of all the disks, and I can get the volume of the entire solid. All right, so we need a few labels in this picture. We'll use a capital R for the radius of this disk, which, so in this picture, that would be how long the strip is. And then we have the volume of the disk is equal to, we do the cross-sectional area, which is pi r squared, and then times the thickness. And let's go ahead and just assume that we're working with x coordinates here. In other words, the thickness we're going to say is dx. Although the imagery here could be rotated 90 degrees, and you could be thinking that these are horizontal strips, in which case you would use dy. So we put the dx here, and then we have the volume of the whole disk. Now the volume of the entire solid will be the volume of the disk, and then we're going to integrate it, get all the disks, and add up all their volumes, and we're going to get the volume of the entire solid. And we just need to know where the first vertical strip occurs and where the last vertical strip occurs. And since we're assuming that we're working with vertical strips, these would be x coordinates. X equals a and x equals b. Of course, if this picture were rotated on its side, these would simply be y coordinates. You would want to find a way to express this radius as a function of x. Once we're doing vertical strips, you want everything to be in terms of x. We want to figure out what the radius is as a function of x, and then square that, and then do the dx. And then these limits of integration would also be x coordinates. Now let's say that we have a region that's not always adjoined next to the axis of revolution, right? So we're still going to revolve around this dotted line, but it's not one of the boundaries of the region any longer. And we still have a vertical strip here. This is all going to be in terms of x, therefore. So the thickness of that strip will be dx. We're going to go from x equals a, which is where the first strip would be, and then x equals b will be where the last one is. This time, though, when you revolve this around, you're going to wind up having a washer shape, and I'll draw the washer shape at an angle. The axis of revolution would be going right through the middle. Well, the volume of this washer is going to be the volume of the disk, the outer disk, minus the volume of the disk that was removed. So we need to label a few things in our picture. We need a radius for the outer edge, and we need a radius for the inner edge. So let's use capital R and lowercase r for these lengths. So the volume of the washer is going to be pi capital R squared dx minus pi little r squared dx. So you could factor the pi out, I'll factor that to the front, and then you can factor the dx out, I'll factor that out to the right, and then we would just have big R squared minus little r squared left and side. And by the way, in this picture up here, little r would be how far the bottom of the strip is to the axis of revolution, and big R would be how far the top of the strip is to the axis of revolution. Notice that in my formula, I'm not using the length of the strip itself. And then the volume of the solid will be the sum or the integral of all the volumes of the washers. And then also, if we're doing vertical strips, then you want to express big R as a function of x, and you also want to express little r as a function of x as well. And so big R is a function of x, and that needs to be squared, and then minus little r is a function of x, that needs to be squared, and then you subtract those in their own parentheses, times pi in the front, put a dx at the end, and then you integrate from x equals a to x equals b. And we have formula for using washers. And once again, if this image on the right, the washers, if this was rotated 90 degrees, then you would just be doing everything in terms of y. All your lengths, your big R and your little r, should be functions of y. Your limits of integration should be y coordinates, and your differential should be dy. Okay, first example. A solid is generated by revolving the region bounded by the curves below, around the indicated axis of revolution, find the volume of the solid. Now, primarily in this lecture, I'm just going to focus on how to set up the integrals, and then we'll use Desmos to actually calculate the integrals. But to begin, if I was trying to find the area of this region, would I use vertical or horizontal strips? What's the easier way to do this? It's easier to do vertical strips on this one because it's always the same upper function, always the same lower function. So draw an example of one such vertical strip at some arbitrary location, and then we're going to revolve around the line y equals 0. So revolving around the x-axis. Now, because this whole bottom edge of the region is on the x-axis, then all of the strips, when I revolve them, are going to produce disks, not washers. So what I like to do is I like to draw an example of one of the disks and then ask myself, okay, well then all I need to know is what the radius of this is. Well, that's given by this length here, which if this were the point P, coordinates would be x, y, and we're asking ourselves how far is the point P from the x-axis? Well, that's just the y coordinate. So the radius, capital R, is simply the y-coordinate. However, we're doing vertical strips, which means that our thickness of each strip is a dx, which means everything has to be in terms of x. Y in terms of x is simply 2 plus cosine of x. So the volume of this disk is going to be pi r squared dx. And in this case, we replace r with this 2 plus cosine of x. That needs to be squared, and then dx. So the volume of the entire solid is going to be the integral of this expression. And we're going to integrate from x coordinate. Very first strip over here on the left starts at x equals 0, and the very last strip is at x equals 2. I like to write the little x equals because it's emphasizing that I'm thinking x coordinates here. And then to do this by hand, you would need to FOIL and then do some trig identities, but I'm just going to go ahead and do this in Desmos, and you get about 39.1, and this is a volume, so it'd be cubic units. Okay, let's do the exact same region. The only thing that's changing is where we're revolving it, around y equals 5 this time. Well, y equals 5 is up here, and we're going to revolve around this line. I'm going to draw an arbitrary strip in here again, and imagine this strip being revolved around this line and what shape it would make. It's going to make a washer, and so I'll draw a little image of what that washer might look like. And there's going to be a gap in the middle. There's a little bit of thickness to it, okay? That thickness is the dx. The axis of revolution is going right through the middle of this. That's the line y equals 5. And in this image here, what we need to know is the big radius and then the inner radius. And so in this picture, the big R is how far this axis of revolution is to the bottom end of the strip, and the little r is how far from the axis of revolution to the top end of the strip. And this point on the curve is like our point P in our exercise from the first slide. So now I want to figure out a few different lengths here. Okay, so the point P, the point that I've highlighted there, which is at the top of our strip, is y units away from the x-axis. Big R. Now imagine this strip being in different locations. Big R is going to be constant because the bottom end of the strip is always the same distance from the axis of revolution, no matter which strip I'm focused on. So big R is actually a constant. So big R is just going to be 5 units. So if I know that big R is 5 units, and the top of the strip is y units away from the x-axis, then that tells me that little r is going to have to be the long length 5 minus that length y. And then, of course, since I'm doing vertical strips and I've got a dx thickness, everything here has to be in terms of x. So little r's can be rewritten as 5 minus, and then replace the y with this expression. So 2 plus cosine of x, which of course you could then distribute. 5 minus 2 is 3, and then distribute the negative, so 3 minus cosine of x will be an expression for little r. All right, so then the volume of the washer is pi, parentheses, and then we do big R, which is 5, and square it, minus, parentheses, little r. Little r is a function of x, 3 minus cosine of x. Square that, close the brackets, and put the dx. This is the volume of the washer. Big R is always 5, but little r changes, right? Imagine different strips, right? If you're up here, big R is still 5, but little r would be something different, changing depending on which x-coordinate, which vertical strip we're on. And then we would want to then add up all of these from x equals 0 to x equals 2, and this would be the volume of our solid. And when I reach for Desmos and do this, I get something about 115.1236 cubic units. Okay, let's do the exact same region, but revolve around a line that's lower than the region, around y equals -1. I'm still going to draw some sort of arbitrary strip, and this time I'm going to finish the problem without drawing the washer. Little r is going to be how far the bottom end of the strip, the closer end of the strip is to the axis of revolution. And big R will be how far the top end or further end of the strip is from the axis of revolution. Now I just have to figure out how to express these in terms of x. Well, imagine all the possible strips, right? If you do all the different strips through this region, the bottom end of the strip is always down here. It's always at the same distance away from the axis of revolution. So that tells me that little r is a constant. It's always 1. It's not changing as I imagine this strip right here being different locations, right? Little r is always 1. But big R is definitely changing depending on which strip I'm doing. And if we have the point P here at the top on the curve, this length from point P to the x-axis is always the y-coordinate. So to find big R, I would want to do that y-coordinate and add 1 to it. And then, of course, you want to write this as a function of x, so just change the y to 2 plus cosine of x, and then add 1 to that, add the 2 and the 1, and say just 3 plus cosine of x. Okay, so then the volume formula will be the integral from x equals 0 to x equals 2, pi times big R squared minus parentheses little r, which is just a constant 1 squared, and then dx. And when you do this one, that's about 69.95 cubic units. Okay, let's keep the same axis of revolution, but this time we're adding another curve to contribute to the boundary. So we added this function here to help change our shape slightly, which is given by this equation right there. So I'm still going to draw an arbitrary strip somewhere in here, and little r will be how far the closer end of that strip is from the axis of revolution, and big R will be how far the further end of that strip is from the axis of revolution. Okay, let's do one of these at a time. As far as big R is concerned, this point is y units above the x-axis, but then we got to go another 1. So it's going to be y plus 1. But we're focused on a y-coordinate of which curve? We're focused on that y-coordinate, so we have to make sure we look to the right curve, and the y-coordinate of this upper curve, that's the 2 plus cosine of x. And so big R is going to be this y-coordinate and then plus 1, 3 plus cosine of x, just like last time. Okay, so now let's focus on little r. Well, here's a different point on a different curve. We know that the length from that point to the x-axis is a y-coordinate, and then there's an extra 1 down here. So little r is going to be y plus 1. But because that's a y-coordinate for a different curve, so I want to use this y-coordinate. So little r is going to be, and this is not yet solved for y, so you're going to want to do that. Divide both sides by 2. And so you have y equals x halves, and that's what you want to place right here. Okay, once you've established those two lengths as functions of x, then you're ready to set up the volume of the solid. It's going to be an integral from x equals 0 to x equals 2, pi, put some brackets. Then we do big R squared, so that's 3 plus cosine of x. That needs to be squared. And then minus, and then parentheses, and then little r squared, which is x halves plus 1. And that needs to be squared. Close the brackets, and then dx. This turns out to be about 61.575 cubic units. Okay, now let's do some regions for which horizontal strips are ideal. If I were to try to think of a vertical strip through here, we do have some problems because through this region, it's one curve defining the top and a curve defining the bottom, but when we transition right there, now we have a different curve defining the top and the same curve defining the bottom. So the vertical strips are problematic. We would have to split our integration right there. We could do it, but let's go ahead and do horizontal strips. Horizontal strips are always the same right and the same left as the horizontal strips go across the region. Plus, we're also revolving around a vertical line this time. So I'm revolving around x equals 0. So this is another reason why we want to do a horizontal strip anyway, because when you revolve a horizontal strip around this line here, that's what's going to produce the shape of a washer. Draw yourself an arbitrary horizontal strip, and we're going to imagine that thing be revolved around this axis of revolution, and it's going to produce the shape of a washer. Axis of revolution is right through the middle of it. Okay, we need to know a little r, which is going to be a horizontal length this time, and we need to know a big R, which will also be a horizontal length. So in their image up here, here's little r, and then here's capital R. Little r is always how far the closer end of the strip is to the axis of revolution, and big R is always how far the further end of the strip is from the axis of revolution. Okay, since I'm doing a horizontal strip, the thickness of the strip is going to be dy. Everything has to be in terms of y. These are going to be horizontal lengths, but we have to write them in terms of y. Let's give these x coordinates different subscripts so I can distinguish them. So we'll call that x sub 1 and this one x sub 2. So which of these curves makes which image in our depiction here? Well, the first one is a line. That's this curve right here. So this little r, which is how far this point is, how far is point P from the y-axis? Well, that's given by the x-coordinate of the first curve. So x sub 1 is that little r. Well, how far is this point from the y-axis? Well, that's also just an x-coordinate, right? X-coordinates are always how far a point is from the y-axis. However, it's this other x-coordinate we're going to be using, the x sub 2. Okay, so we do have to do a little bit of solving because our equations were presented without the x's being isolated. So x sub 1, let's go ahead and find that. Take this 3x1 is equal to y plus 5 and solve it for x1. So we just got to divide by 3. So this tells me that little r is the same thing as x1, which is y plus 5 over 3. Big R is x2. So let's take this equation right here and solve it for x2. Square both sides. We get y squared is equal to x sub 2 minus 1, and then add 1. So we get x sub 2 is equal to y squared plus 1. And that's our big R. Okay, so now we can set up a volume integral. Okay, now when you're doing this, you want y coordinates as your limits. You want to figure out where the first horizontal strip occurs. It happens right here where the two curves intersect. That's a y coordinate of 1. Our horizontal strips start at y equals 1, and the final horizontal strip will be up here, right, which is at y equals 2. So integrate from y equals 1 to y equals 2. We do pi, brackets, we do big R squared. So big R is y squared plus 1, and that needs to be squared, minus little r. Little r is y plus 5 all over 3, and that needs to be squared, and the brackets, and then dy. And everything here is in terms of y. You're going to get a volume of about 22.503 cubic units. So let's take the same region but revolve around x equals 1, which is no longer the y-axis, it's right here. Draw yourself an example of a horizontal strip. Let's call this x sub 1 and x sub 2, like we did last time. There's my little r in this image. Big R is how far we are from the axis of revolution to the outer edge of the strip. This point that's on the left end of the strip is x sub 1 units from the y-axis. The x-coordinate always is measured from the y-axis. Of course, this gap right here is just 1 unit. We would find little r by doing the entire x1 length, but then subtracting from it 1. Now, if I'm focusing on the capital R next to, we have a different curve. x2 is how far that point is from the y-axis, so that's x2. And then, of course, this length here is 1. Big R is going to be the second x minus 1 as well. But now you want to, once again, solve these equations for x1 and solve for x2, which we did before. x1 is the same thing as y plus 5 all over 3. And x sub 2, looking at that second curve in our list, is going to be y squared plus 1. Little r is x1, which is y plus 5 all over 3, minus a 1, right, just following that structure. So big R is equal to x sub 2, which is y squared plus 1, and then minus 1. So in this case, big R simplifies to just simply y squared. Now we can set up the volume integral. The volume will be an integral from y equals 1 to y equals 2, pi times big R squared, so y squared squared minus parentheses little r squared, and brackets dy. When you integrate this, we get about 15.1727 cubic units. And then finally, let's revolve around a line that's to the right of this region, like over here, x equals 5. Draw yourself an arbitrary strip, and the further end of the strip to the axis of revolution is big R, and little r is how close the closer end of the strip is to the axis of revolution. Okay, so we know that the whole length from y-axis to the axis of revolution is a length of 5. Let's focus on capital R first, big R. The point that's helping to dictate where big R is that point here, which is on this curve here. So that's the one that we said was our x sub 1, and this is our x sub 2. So this length right here is x sub 1. So from this diagram, you can see what big R has to be. It's going to be the whole length 5 minus this length here, x sub 1. Big R is equal to 5 minus x sub 1. Okay, now let's focus on little r. Little r deals with this point here. Well, that's our x sub 2. And again, we know that this total length is 5. Little r is going to be 5 minus x sub 2. 5 minus x sub 2. We've already determined what x sub 1 and x sub 2 are. We solved them already a few times. So let's just go ahead and write down what little r and big R are. Little r is 5 minus x sub 2. Well, x sub 2 was y squared plus 1. And when I distribute that negative through there, I'm going to wind up getting just 4 minus y squared. Whereas big sub r is 5 minus x sub 1, and we get 5 minus y plus 5 all over 3. If you want, you could simplify this. I want to show you some things about how to simplify this, just so you don't make any algebra mistakes. But when you commit that subtraction to this fraction here, you're going to want to commit it to the entire numerator. So it really winds up being 5 minus, and I'm going to split this 3 up as well. So we have minus a y thirds and then minus a 5 thirds. And so we really I have to do 5 minus 5 thirds. That's going to be 15 thirds minus 5 thirds. That gives me 10 thirds. So we have 10 thirds minus y thirds. You could just write that as 10 minus y all over 3. And so our volume will be an integral from y equals 1 to y equals 2, pi times brackets, big R, which is 10 minus y all over 3, squared minus little r, which is 4 minus y squared, and that needs to be squared, and the brackets dy. There's our integral, and the volume in this case turns out to be about 14.1488 cubic units. Okay, so there's several examples of how to do horizontal strips and vertical strips both, for finding volumes of solids that are produced by revolving a region around either a vertical or a horizontal axis. Now, you will only produce disks and or washers when your strip is perpendicular to the axis of revolution. When the strips are parallel to the axis of revolution, you're going to produce shapes called shells, which we'll do in the next section.